Okay, this is a video lecture for Math 283. The topic today is vector functions and space curves. We're starting a new chapter. This is chapter 13. This is section 13.1. And to motivate this, let's talk a little bit about the difference between a function and a vector function. So we've all encountered functions for a number of years in our lives now. And a function takes an input, some real number as an input, and it produces a real number as an output. For example, f of x takes x as an input, it produces f of x or y as an output. Okay, and for any given input, we must produce a unique output. We can't produce two outputs for a single input. That's what defines a function. A vector function is related to this. For a vector function takes an input of a real number, as with a function, okay, and we typically call this input t. But its output is not a real number. Its output is actually a unique vector. So that's the difference between a vector function and a function. A vector function takes a real number as an input and puts out and has an output not of a real number but of a unique vector. And we can write this vector in terms of its components as f of t times I plus g of t times j plus h of t times k, and this can also be written in this notation, f of t, g of t, and h of t. So these f of t, g of t, and h of t are the components of our vector function r of t. And t is known as our parameter. Let's talk a little bit about space curves. Space curve is pretty simple. Imagine you had an airplane flying through space, okay? That airplane's trajectory through space would trace out some curve. Or you could have, you could throw a stone that traces out a curve. Or you could have a particle moving in an electromagnetic field, okay? So a space curve is some kind of curve through space. And we need to put arrows here indicating the direction of motion of this particle or object along this curve. Okay, and the object at a certain particular time, okay, how do we locate the object at a certain time? Well, the answer to that is we use a vector function. We use a position vector from the origin up to that point, and we call that r of t, okay? And as the particle moves along this space curve, this r of t will move along this curve as well. The tip of this arrow, the tip of this vector, will move along this curve. The tail is always located right at the origin, but the tip will move along this curve, and we'll trace out a space curve. This is called a space curve. Typically, t here is represented, for a space curve, it would be represented as time t. So more generally, this t could be any parameter, but for a space curve, t will represent the time. So vector functions have a very important and straightforward application to trajectories that an airplane or a particle or some other object might take through space. Now, if we're interested in the point at which this particle is located at a certain time, we would write this point as x, y, and z, and these would each be functions of t. So x would equal f of t, okay, y would equal g of t, and z would equal h of t. So this is how we locate the particle in terms of x, y, and z coordinates at a certain time. Now these are simply, we've actually seen these kind of equations before. These are simply parametric equations. These are parametric equations that specify the point x, y, z and how that point changes over time. Okay, so this is the introduction to vector functions and space curves. What I want to do is consider some simple examples here. And we're going to consider 3 examples. Now, one thing I will say, tracing out space or graphing space curves by hand is difficult. So we're going to use a computer program, an online computer program, to create some graphs. The first example, I'll stay simple though, I'll stay in 2D. So for our first example, what we want to do here is we're going to be given some vector functions, and we're trying to trace out, see what the space curve looks like for those vector functions. So the first example, r of t is equal to t plus 1 times I minus t squared minus 2 times j. Okay, now this is missing a z component, so this is just a 2D vector, which will make it easier to graph. I can write out the x and y coordinates. X is equal to t plus 1, and y is equal to t squared minus 2. Now this isn't always true, but in this case, if we want to see what this looks like, we can actually solve one of these equations for t and then substitute in the other one. That doesn't always work, but in this case it will. If we solve here for t, we get t equals x minus 1. And then we can plug this in the other equation, so y equals x minus 1 squared minus 2. Okay, so this gives us our equation relating y and x to get a sense for what the space curve looks like. Now, this is a simple function. I hope you guys all know what this is. This is a parabola that's been shifted down by 2 units and to the right by 2 units. So let's create a graph of this with our x and y axes. And if we put on tick marks here, let's see, our vertex is down here, and I just want to make sure I get the intercepts approximately right. That's why I'm looking back here. That looks good. Okay, so it's going to come down, our curve is going to come down like this. It's going to bottom out, come up like that. Now, one thing about this space curve is we actually have to add arrows to indicate the direction that the particle travels. And in this case, the particle will start up here and will travel over here. Now, how do I know that? One thing I can do is I can write my vector function or position vector for various times. So, for instance, r of 0, or let's do r of minus 2. R of minus 2, if I plug that in, I get minus I. And here we have minus 2 squared minus 2, excuse me, this should be, I think that should be a plus. Yes, this is a plus. I am sorry about that. That should be a plus there. That was a typo. This comes out to minus I plus 2j. Okay, so the position vector at this time, let's put tick marks up here, goes to this point right here, and we draw this in a different color. So we can draw this position vector like this. Okay, this is r of minus 2. Okay, and then we can also do the position vector at r of 0. Okay, r of 0 equals I. If we plug in 0 for t, we get I. If we plug in 0 for t here for the y component, we get minus 2j. And so this vector will actually point down here, starting at the origin again. This vector is r of 0. Okay, and that actually locates the vertex. And then let's do one more here. Let's do r of 2. And this will equal, let's see, if we plug in 2 here, we get 3i, and we get plus 2j. So I'm just plugging in various values of t here at the time and seeing what my position vector looks like. Well, this locates a point over here, and so now my position vector looks like this. This is r of 2. And so what's happening over time, as you guys can see, if I were tracing the position vector, it's going to swing along like this, it's going to swing down like this, and then it's going to swing up. And this is going to trace out the path of some particle in 2D. Okay, that's a simple example. Let's do a little more complicated one. And this will have to do with a 3D example. And then I think after this second example, I'll cut the video lecture. And then I'll do the third example with you guys live in class tomorrow. So to consider another example, let's plot this curve, r of t equals 3 plus 2t, 5 minus 3t, and 2 minus 4t. Okay, so this is our vector function. and we want to see what kind of space curve we get out of this. Well, we can write our x, y, and z components. X will equal 3 plus 2t, y will equal 5 minus 3t, and z will equal 2 minus 4t. Okay, so those are our x, y, and z equations in terms of this parameter t. Now looking at this, this looks very familiar to you guys, given we just did chapter 12. These are just the equations of a plane, excuse me, the equations of a line, the parametric equations of a line. The parametric equations of the line that is parallel to, so this line is parallel to the vector with direction numbers a, is parallel to the vector 2, minus 3, and minus 4. And also passes through the point this passes through the point. If you guys see what point that is, it's going to be 3, 5, and 2, and passes through this point. Okay, so as this particle moves along, or whatever this object is, it's going to follow a straight line path through 3 space. Now, I could draw this by hand, but it's tricky to draw space curves because it's hard to give depth perception, so I think it would be helpful to use a computer program to plot this space curve. So let's bring that up, and I will bring the video over to you guys. Okay, so this program here is neat. You basically can graph x, y, and z coordinates as a function of a parameter t, and we can animate this. So as we animate this, you guys can see that our position vector, or our vector function, traces out a space curve along this straight line through 3 space. Okay, and that's cool. And the sense of this is that it goes from up top here down to the bottom here. So as t progresses, it goes down along this line. Okay, let's animate that one more time. So this is a simple space curve. Tomorrow in class, I'm going to consider, I will consider a couple other space curves. I'll do a couple more example problems, and then we'll do some practice problems. So I'll see you guys tomorrow in class.